Now we shall study second chapter from this paper of real analysis part first, from the book Methods of Real Analysis by R. Goldberg. The chapter is Sequences of Real Numbers. First we shall define sequence, also subsequence. Then we shall define limit of a sequence, and then we shall consider types of different types of sequences and theorems related to sequences. So first we shall define sequence, and then we will consider example of sequence. A sequence which can be denoted by S, Sn, n takes value from 1 to infinity. This is notation for sequence. Sn, n takes value 1 to infinity is a function. Is a function from the set of all integers or set of integers I to the set of real numbers, and that is denoted by R. The sequence we have denoted by S is equal to Sn. So it is function from set of integers to set of real numbers. So we have S is equal to Sn, n takes values 1 to infinity, and as n is equal to 1, n varies from 1 to infinity, we get S1. n is equal to 2, we get S2. n is equal to 3, we get S3, and so on. For n, we have Sn, and this is continued up to infinity. So Sn is called the nth term of the sequence. And a sequence can also be denoted by another notation also, say Si, I takes value 1 to infinity, Sm, m takes value 1 to infinity, etc. Now we will consider a subsequence. A subsequence of a sequence. The sequence Sn, whose terms are S1, S2, S3, and so on, is usually denoted by there is a notation for this Sni, and here I takes value from 1 to infinity. So you should note this, how the subsequence is denoted by the notation Sni. Subsequence is a similar concept to subset. So that means subsequence will have terms from the original sequence. Few terms are taken, or that may also be infinite, but the selected terms are taken in subsequence, and these are denoted by Sni. So if I is 1, we get S1, Sn1, I is 2, Sn2, and Sn3, and so on. General term is Sni, and so on. So thus this is a subsequence of the original sequence Sn. Now we shall consider example, then it will be clear. So consider example. Consider a sequence. We will have a simple sequence Sn is equal to n. n takes value 1, 2, 3, etc. Or that means the sequence is Sn as n takes value 1 to infinity is equal to n. Sn is n takes value 1 to infinity, and this will generate the sequence n takes value 1, 2, 3, 4, etc. or actually this is a sequence of positive integers. And now we will form its subsequences. The sequence, see, we can consider the odd integers, and that will be the subsequence of this Sn, or we may consider this as sequence 1. 1, 3, 5, 7, etc. is a subsequence. Subsequence of this Sn, or we simply write n takes value from 1 to infinity. Now you observe the terms of this subsequence. Subsequence is also a sequence, but the relation is it is a subsequence of this original sequence. Yeah. And the terms are 1, 3, 5, 7. Now how the terms are defined, it can be denoted by with this notation, you see, Sni. Sni, I takes value 1 to infinity. Here n takes value 1 to infinity, but here I takes value 1 to infinity. Where ni is equal to 2i minus 1, because these are odd integers, and odd integers are given by 2i minus 1. I takes value 1, 2, 3, etc. integers. And now you see, therefore, what is a Sni sequence? I takes value 1 to infinity will be equal to Sn1, Sn2, as here we have written Sn3, and so on. And this is equal to Sn1. What is n1? N1 is, put I is equal to 1. So 2 minus 1 means 1. N1 is 1. So S1. What is N2? Put I is equal to 2. N2 is 2 into 2 minus 1, that is 3. And therefore it is S3. And what is N3? I is 3, so it is 5. S5. And so on. Or now from this original sequence we have to refer. This is S1. S1 means here it is original sequence is this one. So 1. What is S3? Third term, that is 3. And 5. S5, that is fifth term, that is 5. And so on. So this is the choice of the terms for subsequence. So this is a subsequence. This is a subsequence of the original sequence. Another example can be considered as, say, the sequence of even integers, even positive integers, is also a subsequence of the original sequence of positive integers. So second example, this sequence, say 2, 4, 6, 8, etc. is a subsequence. Is a subsequence of the sequence n. Now how to denote it? It can be denoted by, or it is denoted by Sni. I takes value 1 to infinity. The same notation we are using, where what is the choice for Ni? Ni here we have picked even integers from the original sequence, and therefore this Ni should stand for even number, that is 2i. Even numbers are denoted by 2i, odd numbers are denoted by 2i minus 1. I takes value 1, 2, 3, etc. And therefore we will have here Sni. I takes value 1 to infinity is equal to, see, Ni, I is 1, so it is 2. Put I, very I is 2, that is 4, S4. Next term I is 3, S6, and so on. And this will give S2 means second term of the original sequence, that is 2. S4 means fourth term of the original sequence, 4, and 6. So this is also a subsequence of the original sequence, and thus In general, the subsequence is denoted by SNI. This notation for subsequence. The notation for original sequence is SN. And N1, N2, N3 are such that N1 is less than N2, N2 is less than N3, and so on. These are arranged in order. Now there is one example from exercise we will consider. That is others are simple, but we shall consider this example. So this is the example from the exercise 2.1. I should first write the problem here. Let Sn is equal to, or the sequence, yes, be the sequence, or in the notation Sn, n takes value 1 to infinity, be a sequence given by Sn is equal to 2n minus 1. And now we shall find few terms, say S5, S9, and say N1, N2, N3, SN4, SN5, and so this is an example. Now the solution for this. What is given here? Sn is 2n minus 1. So actual terms of the sequence will be like this. Sn is a sequence from 1 to infinity, and that is 2n minus 1. Sn is 2n minus 1. So therefore this is 2n minus 1, n takes value 1 to infinity. This will generate all the terms of the sequence, and first term put n is equal to 1, so it is 1. 2, so it is 3. Further 3, it will be 5, that means it will be a sequence of odd integers, 9, etc. Now what are asked to find? S5. Now here Sn is 2n minus 1. From this Sn we can get any term of the sequence by substituting the value of n. So we are asked to find S5. So what is S5? It is 2 into 5 minus 1, or which is 9. What is S9? S9 is 2 into 9 minus 1, or that is 17. And now what is N1? So we should consider the N1 here, but for that N1 is to be defined. Let Ni is equal to I square. I takes value 1, 2, 3, etc. So this is Ni. Ni may be defined by any expression. Here it is defined as, earlier we have defined Ni as 2i. Now here it is I square for this problem. And then find now N1, N2, etc. So we can find further, given Ni is equal to I square. I takes value 1, 2, 3. So what is N1 from this? N1 will be 1 square, that is 1. N2 will be 2 square, that is 4. And N3 is say 3 square, and that is 9. So etc. we should. Now it is asked N4. So for that we first find N4 and N5, then we will find Sn4 and Sn5. So what is N4? N4 by this 4 square. We have to use the respective definition. For Ni, it is I square, and for Sn, it is 2n minus 1. N4 is 4 square, or which is 16. What is N5? it is required for obtaining the term of the sequence. Yes, n5 will be say 5 square, that is 25, and therefore Sn4 is equal to n4 is 16, s16. And what is s16? For s16 we have to look for Sn definition. So 2n minus 1. Here n takes value 1, 2, 3. And therefore S16 is 2 into 16 minus 1, or that is 32 minus 1, 31. So using first definition, or we may suppose this as 1 and this as 2. So these are obtained, n2, n3, etc. are obtained by 2. And here, so this is obtained by 1. Also we can find out n5, and that is n5 is 25, and therefore from 1, that is 2 into 25 minus 1, or that will be 49. So this is by 1, and thus we can obtain the different terms of this. Now actually what is the subsequence Sni here for this problem? The subsequence Sni will be I takes value from 1 to infinity is yes ni. What is ni? I square. So we may write this as yes I square. I takes value 1 to infinity, and therefore actually the terms of Sni will be yes I square s1 square, that is s1, s2 square, that is 4, and 3 square, that is 9, 5 square, that is 25, and so on. So this will be the sequence, and we can write the terms of this also. What is s1? S1 now you see from this, it is 1. What is s4? We have calculated here s4, where we have not obtained, but s4 can be replaced. 2 into 4 minus 1, that is 7. S9 is obtained, that is 17, and S25 here we have S25, that is 49, etc. So this is the subsequence of this sequence, odd integers. All these are odd integers, and obviously Sni is a subsequence of the set of integers, that is sequence of integers. So this is Sni. There is the equation whether this is a subsequence. This is a subsequence of k. K takes value 1 to infinity, or which is 1, 2, 3, 4, etc. This is a subsequence of this sequence. This is also a subsequence of this sequence of integers. So this is the relation between sequence and subsequence, and how to obtain the terms of a sequence. It is easy. Sn will be defined from Sn. Put n is equal to 1, 2, 3 as required value. That will generate all the terms of the sequence. Similarly, for subsequence, ni will be defined, and put I is equal to 1, 2, 3, etc. We will get ni value, and then put ni value in this, and then we will get the original sequence term S16. And for that we have to use 1. So both we have to use. For actually the subsequence is a composite function. First we get ni, and then we get use Sn value, and that generates the subsequence. So this is about the notation of sequence and subsequence. The next concept is limit of a sequence. Now we shall define limit of a sequence. First we shall earlier we have defined as a sequence is a function, and we know how to define limit of a function. So similarly there is a limit of a sequence. So limit of a sequence For this, we write the definition. Let Sn be a sequence. And here we are considering sequence of real numbers only. Then Sn, we say Sn approaches to a limit L, and here L is approaches, or we can say Sn has a limit L. Approaches to or has a limit L, where L is a real number if for every epsilon greater than 0, for every or any, epsilon is a Greek letter, small number, real number, positive, which is greater than 0. For every epsilon greater than 0, there exists, or there is a positive integer n. That means n will belong to I such that absolute value of Sn minus L is less than epsilon, n greater than or equal to n. And we write this as limit of Sn as n tends to infinity is equal to L, or Sn approaches L as n approaches infinity or tends to infinity. So this is the definition of limit of sequence. Sn is a sequence. We say Sn approaches to a limit L or has a limit L, where L is real number if for every epsilon greater than 0 there is a positive integer n such that absolute difference of Sn minus L is less than epsilon whenever n is greater than or equal to n. So this is important condition for limit. When the sequence has limit L, if the difference or absolute difference of Sn and L is very small, that is the meaning of this, and for n greater than or equal to n. Absolute difference of Sn and L is very small, or that means distance, geometrically it is distance between Sn and L, and that is less than epsilon, very small. So mod of Sn minus L we can consider as, say, mod of, so what is the mod of 7 and 3 difference, modulus of 7 minus 3, or this will be 4. Or other way we can consider 3 minus 5, that is 2. Or this can be said as the distance between 7 and 3 is 4, or distance between 3 and 5, absolute distance we have to consider positive value, and that is equal to 2. So this Sn approaches L means becomes closer and closer to L. Then the distance between Sn, or the difference between Sn and L, is very, very small. Epsilon is a small integer, small number, not integer, it is a small number but positive, epsilon greater than 0. Now we will consider examples related to this. So first we will have this sequence examples first. The sequence we shall consider notation as Sn. N takes value 1 to infinity, given by, or where Sn is equal to 1 by n, has a limit or has the limit 0. Now you see, we shall prove this result. We shall prove this result using the definition. So given sequence will be Sn, n takes value 1 to infinity, or that can be written by putting the value of Sn. N takes value 1 to infinity, or it is 1 by 1, that is 1, 1 by 2, etc., 1/3, 1 by 4, and so on. In general, 1 by n, and it will be continued. And obviously we can see as the denominator goes on increasing, the value becomes value will decrease and it will approach towards 0, and therefore this sequence has limit here, that is L is equal to 0, and we have to show now here Sn is, we have to we know the limit and we have to show according to the definition. Now Sn is 1 by n and L is 0. So therefore, to show this by definition, we have for every epsilon greater than 0, we can find, or there we show that there is an integer n such that this condition holds, or this condition is true. So given epsilon greater than 0, we have to find n. N are a positive integer, n belongs to I, such that Sn minus L is less than epsilon, or n greater than or equal to this capital N, positive integer, or a certain positive integer onwards. Now if capital N is say 4, it will mean that n greater than or equal to 4 means after fourth term of the sequence. Then the distance is very small, within less than epsilon distance. So that is, or therefore we can say, we shall put the value of Sn. Sn here is nth term of the sequence, which is 1 by n. And L, the value of L is 0. So this we have to show is less than epsilon for n greater than or equal to n. So if we find n like satisfying this condition, then we can say that limit of this sequence is 0. But you see, what is the mod of 1 by n? Mod of 1 by n is 1 by n itself, because n is positive integer and say n takes value 1 to infinity. Therefore, its absolute value is the same. 1 by n is less than epsilon. N greater than or equal to n. Now we suppose this as second. Now the second inequality holds if you select n is equal to capital N. Now for n capital N, for the choice of capital N such that this 1 by capital N is less than epsilon, then